Okay. So we started talking about the curl, which is the differential form of the circulation. And essentially, we did our usual trick that we like to do. We like to always go back to the fundamental theorem of calculus. So the curl is some sort of, we tied the divergence to the volume integral. We tied the gradient to the line integral. We're tying the curl to the surface integral. And any surface, really, any surface that you have, and you have a field F, and you're integrating the field over that surface. So you have SF.ds. The trick is now, this is an integration over the medium. You want to tie it to integration over the boundary. What's the boundary of a surface? The boundary of a surface is the contour around that surface. The line that is the represents the contour around that surface, the curve around the surface. So I want to tie this surface medium integral to the integral on its boundary. The integral on its boundary is just a closed line integral of, well, of something that I can get from F. So how did I do that? No, let me do it. Yeah, we do it this way. So the boundary integral, which is F.dl, it's tied to the surface integral. And what we have here, what we integrate here, is something that we can get from F, to some sort of operator. That operator is the curl F. Okay, and that's it. This form of the fundamental theorem of calculus in this way that looks like that is called Stokes theorem. I mean, it's called a theorem, but it's a really, as we'll show later, it's a really obvious statement. But it's called Stokes theorem for historical reasons. And that's enough for us to define how to calculate the curl and try to interpret what the curl is. And the trick now is to shrink. So I take this area with its contour around it, and I shrink it to a really small area. When I shrink an area, it has an orientation. So it has an orientation ds, right? So this is in some direction. U hat is or let's call it n hat. We call it n hat. The normal to that area times delta s. Right? It's this sort of vector. So the idea is that when we have a really tiny area, I can take this thing out of the side of the integral. Because I can take it outside of the integral, this becomes curl F. And then I can take n outside of the integral, because n is constant. And what remains inside the integral is the surface area delta S, is ds essentially, is the sum of this area, which is just delta S. So the sum of the whole area is just delta S, right? Equals, this is of course as delta S goes to 0, F.dl. So this tells me I can divide delta S, take delta S to the other side. So this tells me that the curl is a vector field. If I have a vector field, I take this curl, I get another vector field. If I dot this vector field in any direction, what I'm doing is I'm figuring out what the circulation is in that direction. Essentially, I'm trying to figure out in direction n hat, how well does this field rotate around this axis? That's what I'm trying to measure, right? So this is going to be the limit as delta S goes to 0. Okay. This is essentially how you calculate the curl. And we can use this to derive even further. We can use this to derive formulas for the curl that are dependent on the coordinate system. So if we label everything in space with using a coordinate system and we have our basis vectors at every point, we can calculate the curl at every point using a formula that we can derive from this definition or result. I mean, it's a matter of choice. I like to think of Stokes theorem as the fundamental property, and then you derive the definition of the curl from Stokes theorem, right? But we don't want to stop here. We don't want to stop with just the mathematics of it. So remember in the divergence, we discussed how to calculate the divergence, but we wanted to get like a bit of an interpretation of what the physical interpretation, geometrical interpretation of what the divergence is. And the divergence turned out to be one way of thinking about it is that any field F I can decompose into let's say I have a field around a point P, and then I have the field at that point F at P. If I zoom enough, the fields at the adjacent points are going to be equal to FP. Right? If I keep zooming in, kind of like in calculus, in differentiation, when you zoom in, it becomes a straight line. So what happens when you zoom in, the fields around P become really similar to F at P, right? But there is some difference. There is some infinitesimal difference between them. There is some variability, right? It's not going to be exactly the same field, but the difference is going to be infinitesimal as we zoom in into that point. And that infinitesimal difference divided by the infinitesimal area or volume is going to give me this sort of differentiation. So the idea I can write F in all of space. This is F in all of space as F at P plus F delta. F delta is just how the field at every point in space is different than F at point P. Right? Why do I want to write it like that? Because in that case, and this argument, by the way, follows for divergence too. You can go back to the divergence and try to understand it using this argument. So if you take the curl of F, from the formula has an integral in it, right? Integral is linear. If I have F equals A plus B, I can distribute the integral over A and B, right? So curl F, which is FP, which is curl F at P, which is the constant over all of space, plus F delta, right? I can distribute the curl. I can do the same for the divergence, by the way, and the gradient, right? This is obvious because it's all based on integration. So divergence U plus V is divergence U plus divergence V. I hope this is obvious because in the definition there's an integration, and you can always distribute the integration over addition. Integration is linear, and henceforth gradient divergence is linear. So divergence of A plus B is just divergence of A plus divergence of B. Same thing with the curl. Curl of FP at plus F delta is just going to be curl of FP plus curl of F delta. But FP is the constant vector field, right? And the curl and the divergence of the gradient are all differentiation operators. So what should happen if you differentiate something that's constant? It's going to be zero. This whole thing is going to be zero. You can even go back to the definition here, formula here, and you can see if F is constant, the circulation of any constant field is obviously zero, right? You're going around the contour, and the field is constant everywhere. Obviously, is going to be zero, right? So what we end up with is that curl F is just the curl of F delta. Right, so we can understand what the curl does, but by just looking at what the curl does to the infinitesimal changes in the field around the point P. So we have a point P, and at point P we have F of P at that point, and then the curl gives us an understanding of what the infinitesimal changes of the field are around that point. Now, curl F delta is a vector. Since curl F delta is a vector, we can always decompose it. Any vector, you can decompose it into two vectors, right? You can decompose, you can do this decomposition. I can decompose any vector into three vectors that add up to that vector. But here I want to decompose the curl. It's a vector. Unlike the divergence, which was just a scalar, this is more complicated. This is a vector. So I can decompose it into a component that is in the direction of F of P. So this is curl F delta. That is, let me write it this way, parallel to FP, this vector here, and I can decompose it to another vector that is normal to FP. So curl of delta is normal to FP. So what do both those two components do? Okay, what does circulation parallel to FP mean? Well, let's kind of look head on. Let's change the perspective. Let's look head on. So this is a dot. This means that the vector FP is pointing towards the screen, right? The circulation, from the definition, this is just the circulation. So the direction, this component is of the curl is in this direction, right? It's a circulation around the field. So it's going to be something like this. So this is going to be, this is what the component of the curl on that plane looks like. It's going to be something like this. This is going to give me a circulation, right? This is the infinitesimal changes in the field around point P. What does this equivalent to? Let's say I have a field. Let's go back to the side view. I have a field, and then I have this small infinitesimal change. Okay, this is a twist. This is a bend in the field. The field bended like this, right? But then the bend is circular. So what happens if you have a bunch of fields around FP? So this is FP, and then you have a bunch of field lines around FP, and each one of those this bends this way, this bends this way, this bends this way, this bends this way. It's like a twist. So this is like a twist. Imagine a cable, and you hold the cable. So you hold the cable of, imagine strands of wire that you lump them together, and then you twist them. So you apply a twist. You get something like when women braid their hair, you get something like a braid, right? So this is the sort of infinitesimal action that the curl is. This is the sort of deformation of the field that the curl is encoding in this case. It's a twist. What about the normal component? When the normal component, we're looking at the side view. So this is going to be FP. F at P is going to be this arrow, FP, and this is point P, right? So this is circulation that is in the plane of F, where F exists. So the circulation is going to look like this. This is what this is doing. So notice what this is doing. If the field that is next, that is to the right of FP, is going to be increased a little bit. See, the arrow is pointing that way. So the field is going to be increased a little bit. And then on the other side of FP, the field is going to be decreased a little bit because the arrow is going in the opposite direction. So the field is going to be decreased a little bit. So this is like a shearing of the field, where the field is changing, but it's changing, on the normal plane. If you walk on the normal plane of the field at a point, the field increases or decreases. So this sort of action is like taking, it's like two tectonic plates that are moving against each other. This sort of thing is called the shear. Okay. And of course, there is twisting, because if you look above a bit, the field above this field a little bit is going to be twisted this way. The field below a little bit is going to be twisted the other way. So there is twisting in this direction, but there is shearing in the what's called the transverse direction. Okay, so this would be like kind of like the intuitive interpretation of what the curl does. The curl represents a measurement of how the field twists and shears, while the divergence represents a measurement of how the field compresses and expands, converges and diverges. Of course, this is infinitesimal. This is all infinitesimal. This is all like a tiny amount of change at a point. This is mathematics. In the physics, if we go to the physics, we will find out that an important field, for example, is the electrical field. So I could have an electrical field, or I can have a magnetic field. So I could have magnetic lines of magnetic field, B, let's say. We found out, like experimentally, that and the mathematics were developed later, that you could do this sort of twist of those field lines. So the field lines twist, twist like that, twist like a braided hair. And what induces that sort of twist? If you have a current flowing, if you have an electrical current flowing. So I'm just tying this back to the physics. At this point, we are just doing the mathematics of it. But this is how I would interpret the curl geometrically. Now, yeah, that's a little bit hairy. Compared to that, it's always difficult to visualize things in 3D. Compared to that, calculation is easy, because that's why people just jump directly into calculation. Computing the curl is easy. You just apply the definition. But before you can compute the curl, you have to lock down a coordinate system. So for the Cartesian system, of course, any field can be written in terms of x hat and y hat and z hat components, right? So curl F is a field. So we're interested in finding the x, y, and z components of curl F. So curl F, excuse me, curl F is going to have an x component, a scalar, times x hat. Curl F is going to have a y component, y hat. Curl F is going to have a z component. So really calculating curl F, because curl F is a vector, we have to calculate its components that go with x hat, y hat, and z hat. How can we do that? Well, that's easy, right? I can just take this and dot it with I can just take curl F and dot it with x hat. What does this give me? This gives me this component, right? Because if I dot this with x hat dot x hat gives me 1. X hat dot y hat gives me 0. X hat dot z hat gives me 0. Right? So this is the way you get to the x component of the curl. You just dot it with x hat. You see that? Just take this and dot it with x hat. So that's equivalent to dotting all the terms with x hat. This gives me 1. This gives me 0 and 0. Right? 1 times the x component. So this gives me the x component. We already defined this, right? This is just the integral, of course, limit as d delta s. Sometimes I ignore the delta s, the limit. I assume that it's small, right? F dot dl over delta s. Okay. Now this is an infinitesimal area. I can take it to be anything. I take it to be the easiest thing I could think of, which is just a square. I take this to be a square, infinitesimal square. So if I go to my 3 dimensions, I have a point here. This is x hat. I will take my contour that I'm integrating over to be, I'm going to draw it big, but imagine it to be really tiny, right? But just so that we can draw it easily, I'll draw it big. Imagine it to be this rectangle. This is the contour, right? This is delta s. The distance from here to here is delta y. The distance from here to here is delta z, right? So this is normal. This is the area normal to the x hat vector at that point, at point P. Right, and this is an infinitesimal area. So the idea now is that I can easily calculate this integral here, right? It has 4 sides, so I just integrate 4 sides. So let me start with this side. So this side is essentially the value of the field. What is parallel to this contour? So this is a dot product, right? And this path is only parallel to the fz component. So here I have fz z hat, right? Fy y hat is when I dot it with this path is going to be 0 because it's perpendicular to this path. Same thing with fx x hat. The only thing that's going to contribute to the line integral along this path is f z hat, right? Same thing on the other side, right? The only thing that's going to contribute to the line integral on this path is minus f z hat. The only thing that's going to contribute in this direction is just going to be fy y hat. This is going to be minus fy y hat. I'm writing the components of the field in every part of the path that are the sole contributors to the integration along that path. Right, dotting x hat and z hat and y hat along this path here is going to give me 0. So taking it one at a time, this is going to give me. So here I'm at delta y away, right? So this is going to give me only f of z is contributing. So this is going to be f of z x y plus delta y z, right? So I'm going to start with this and this. 1 and 2, 1, 2, right? So this is going to give me, I need to multiply it with the distance. What's the distance? Delta z. This is going to be delta z. Okay, this is the integral along path 1. The integral along path 2 is going to be the same, but I'm going to have a minus sign, and it's going to be delta y in the past. So it's going to be, there won't be the delta y, so it's going to be minus f of z x y z, again delta z. Right, and then I have to do now this 3, this segment, and 4, this segment. So that segment is going to be well. I'm going to start here. It's going to be positive, but let me take a negative sign out. If I start with 4, it's going to be negative. Let me take the negative sign out. So this is going to be fy at x, y, z plus delta z, see that, times delta y minus fy x, y, z times delta y. Now the whole thing, both of those terms are divided by delta s, which is delta y times delta z. So what does this give me? Delta z cancels out. I end up with fz x y plus delta y z minus fz x y z. The whole thing is divided. Delta z went away, delta y. And then I take the other term, which is fy x y z plus delta z. Delta y goes away, minus fy x y z. Delta y goes away, I end up with delta z. This is the definition of differentiation, partial differentiation, right? Because fz is a function of multiple inputs, right? Multiple variables. So we know what this is as the limit goes to, as the surface area goes to 0. This is essentially delta fz over delta y partial minus delta fy over delta z. So you end up with this curious thing, right? And you can repeat this, by the way. So you can repeat this. So this is curl f dot x. You can repeat this for the other two basis vectors, y and z, and you'll get similar looking expressions. So curl f dot y is going to be delta fx over delta z. I'm going to show you how to quickly get those expressions in a moment. Delta f typo here. Okay, delta fz over delta x, and then curl f dot z is going to be delta fy over delta x minus delta fx over delta y. There is, remember when we were talking about the cross product, we talked about a certain permutation symmetry that appears. In this situation, this exact permutation symmetry appears again. And I'll show you what I mean. So for the basis vectors, there was this symmetry. You go from x to y, from y to z, and then from z to x. So this symmetry appears again and helps you to write down the curl easily. Really, you don't need, some people, do this curl as a determinant to help you remember how to write it down. But you don't really need any of this business. I mean, you can look at the determinant definition if you want to. It's just to aid in remembering the curl. The curl is not a determinant at all. Determinant has nothing to do with the curl. This is just a shorthand to try to remember the formula for the curl. So let me show you how to write it down. So I have curl F. The trick is that the curl is going to have an x hat component. So you go back to this nifty permutation diagram, permutation graph. And then that permutation graph is going to give you the denominators of the partial derivatives. So it's going to be a difference between two partial derivatives. So what comes after x? Y and z. So you're going to have a delta y here and a delta z. And then where you put the components, you just invert the denominators. So here, instead of fy, I put fz. Instead of fz, I put fy. So the permutation graph gives you the denominators of the partial derivatives. And then what goes on the top is an inversion of what happens in the denominator. That's how you easily write down the curl in an instant, right? So let me show you. Let me do y hat component. Y hat component is going to be, again, what comes after y? Z and x. So I'm going to have a delta z minus something over delta x. And then I invert. So the f here is going to be delta. Oh, there's a delta here. Of course, there's a delta. So f here is going to be fx and then delta fz. Notice the inversion. And then the z component. Again, the denominators are z. What comes after the z in the permutation graph? After z comes x and y. So I'm going to have delta x and then delta y. And then I invert the components. Delta fy over delta x minus delta fx over delta. This turns out to be the formula for calculating the curl of the field at every point in space. If you have the field f, and someone asks you to compute the curl, this is how you would go about doing it. What about other coordinate systems? Well, this is very similar, and it's one of those things that I keep saying you have to do once in your life. I did that once in my life. It was fun. Right? The curl is going to be the same as a vector, regardless of the coordinate system. The component values might be different because you have a different coordinate system, but as a vector that you draw in space, it has to be the same. If it turns out, if you change the coordinate system and you get a vector that you draw in space that turns out to be a different vector, you've done something terribly wrong. So the way you do that is you need to transform the operators and you need to transform the basis vectors. And this is something we know how to do already. It is cumbersome. It's a lot of algebra. But if you go through the exercise once and then put it in your notebook or in a table that you revisit when you do those calculations, the same permutation graph applies, by the way. So for cylindrical coordinates, the same permutation graph applies. So for cylindrical, we start with R, go to, what's the next one? After R, it's phi, and then the last one is Z. So this same permutation graph applies. So I can write this curl as follows. So it's going to have an R hat component. It's going to have a phi hat component. It's going to have a Z hat component. And then I could write down the partial derivatives. So what happens? What comes after R? Phi and Z. So I put in here delta phi, delta Z minus. Let me do the other ones. What happens after phi? Z and R. So there's a delta Z and then minus something over delta R. What happens after the Z? R and phi. So there's something over delta R minus something over delta phi. So that's good. However, And we could say here, we invert on the numerator. So I have delta AZ. Oh, I was doing, why am I doing? Oh, I have some, because I was doing the notebook, the textbook sometimes uses A. So I'm using F. So I'll remember to correct that. So delta FZ, delta FE. I'm writing this as if it's a Cartesian coordinate system. It's not, so things have to change a little bit. But this is the basic structure: FZ, delta FE, delta FR. Our basic philosophy of using the permutation graph and then inverting in the numerator. But that's not enough now, because this is a cylindrical coordinate system. So we have to do, it doesn't make sense for us to have the exact same formula as the Cartesian. So there has to be some corrections. The corrections are as follows. It turns out to be a 1 over R here. That's the first correction. The other, the phi component, the phi hat component is the same, scalar component is the same. However, the z hat component, there's a factor of 1 over R here. And then instead of differentiating f phi, we differentiate R f phi. So there has to be some corrections peppered in to accommodate something that's different than the Cartesian system. And then finally, for the spherical system, the formula is like this. There's an outer, there's 1 over R sine theta, and then there's delta A phi sine theta, sine theta. So it's a little bit more complicated. But after R comes theta and phi, so it makes sense. I'm going to have theta here first, and then a phi. And it's going to be something like that. Let me write it down quickly. 1 over R, 1 over sine theta. Notice it's a little bit more complicated. Delta AR over delta phi. Phi comes after theta, so that makes sense. Minus delta R A phi over delta R theta hat. And then 1 over R delta R A theta over delta R minus delta AR over delta theta phi hat. Right after phi comes R and theta. A sanity check whenever you're looking at this form. Let's say someone gives you a formula and you're not sure if it's wrong, right or wrong. One big sanity check you can always, doesn't guarantee that the formula is right. One big sanity check has to do with the units. Because here, everything we're differentiating with respect to distance, with respect to displacement. So notice here, wherever we have corrections in the Cartesian system, y, z, and x represent displacement in space, distance in space. Theta is an angle, is not a displacement. So there has to be always some correction to change this coordinate change that is not a distance to a distance. So delta theta is not a distance. How you do change it to a distance? You multiply it by R. Right? That's a general rule of thumb, but it doesn't always apply. For example, it's not obvious why you need to multiply F. Well, yeah, it's obvious why you need to multiply delta R F phi by R, right? But no, sorry, it's not obvious. Why? Because I already have R in the denominator. It seems I'm adding an extra R here. So if I'm have an extra R here in the numerator. I'm adding a dimension to the numerator, multiplying the numerator by distance. But this is all okay because I'm canceling it out because I have the divide by R here, right? And here I don't have to multiply by R because I have already the R here outside, okay? So this is a sort of sanity check. It doesn't give you the formula exactly, but it tells you if a formula smells funny, if it cannot be right. All right. So that's it. We introduced the three sorts of differential operators. We introduced the gradient of a scalar field. We introduced the divergence of a vector field, and we introduced how a field would converge and diverge. And then we introduced the curl of a vector field, how a field twists and shears. And those are three valid differential operators. Why do we have more than one differential operators? Because we have 3 dimensions. So there are 3 ways really things can change rather than just one way. In this treatment, I gave you what ultimately is called the divergence and Stokes theorems as a priori facts, as postulates, as the thing where you begin to define the gradient and the divergence in the curve. You can look at this from the other perspective. We could look at so we looked at the integration in the medium, and we assumed that this has to be equal to some integration on the boundary. We could look at it from the opposite perspective. We could look at an integration on the boundary and then try to divide that integration up over the underlying region. So let me show you what I mean. So let me write down the 2 main theorems that I kind of like just, written down as obvious. And I'll show you why I think they are obvious. So let's start with the divergence theorem. The divergence theorem says if you integrate over a volume of a divergence of a field f dv, you get the surface integral over the boundary. This is called the divergence theorem. And you can geometrically represent it as that. I can draw a volume like that. This is a volume V, have a field F, and then I can imagine the surface boundary. This is S, the surface. Let me draw it red. So this is the boundary of that volume. It's the outer shell of that volume. So if I have a field F and I could take its divergence, if I integrate the divergence over a volume, right, this will equal that. And the other theorem that we again introduced as a postulate, which is called Stokes theorem. So this is if you integrate a curl over a surface, this is going to equal the line integral over the boundary of the surface. So I draw the surface something like that. It's hard to see, but imagine this like something coming out of the soap bubble, the thing. So the rim of a soap bubble, and this surface, this is the soap bubble being some kid is blowing into this, right? Right. So this is the curve L, and this is the surface S. And this fact is Stokes theorem. So we started this in a reverse manner. So I assumed I have the volume integral and assumed I can write it as an integral on the surface. But I can take the opposite perspective. I could look at a surface integral, right? The surface integral is a flux, essentially. It's the flux of the field. So I have let's say a big surface. Right? And this is Stokes. Let me start with Stokes. Actually, let me start. Yeah, Stokes start. So this is not a surface. This is a curve. This is a big curve, closed curve. Okay. So I want to start from the opposite perspective. I want to start with the integral on the boundary. So let's see. So I have f dot dl. Right? So I have a field F. I can always intuitively take this circulation on this curve and divide it into multiple tiny circulations. So let's say I cut this in half. So instead of having this big circulation, I have a circulation going from this point, reaching here, and then going back. Right? Something like that. And then I have another circulation starting from this point, going in this direction. It's exactly on top, and then going this way. Right? those two circulations, the sum of them is exactly equal, right? So this circulation and this circulation are exactly equal to the bigger circulation. You see why? Because I'm moving here, because the circulation in this path that's touching, this is touching, is opposite of each other. So everything cancels here. Right? What's remaining is the outer edge. And I can continue with this. I can divide this into smaller and smaller and smaller circulations, all touching, all filling the area in between. But if let me zoom in here. But when I zoom in, everything that happens on the boundaries cancels because everything is opposite, right? So this circulation is opposite to this circulation. So at their boundaries where they're touching, everything cancels. You have something going, clockwise, and the one next to it is going counterclockwise. They cancel each other. Well, both of them going clockwise, but here in this region, they meet with opposite directions. So clockwise, this is going here this way. Clockwise for the next one going this way. So everything naturally cancels except what remains on the boundary. And if you look at this, if you divide this, you can take this and you can divide it into the sum of those tiny circulations. What are those tiny circulations? Those you sum over those tiny circulations. What's the sum? It's an integral. You're summing over a surface. So this becomes a sum over a surface. What are those tiny circulations? Those tiny circulations are the curl, right? From the definition of the curl is a tiny linear circulation, right? From here. The curl is a tiny linear circulation. So it's obvious that this bigger outer integral is just the sum of those tiny circulations, curl F dot over the whole surface. This is obvious. And why is it obvious? Because those tiny circulations all cancel at the boundaries. Everything telescopes to the boundary. That's the boundary is the only thing that remains. Right? And the same thing, the divergence theorem is obvious because you have here a surface, this is a volume. And then I have here a flux on the surface. So this is surface S. The flux on the surface is a closed integral S FdS. And we can divide this volume now into small volumes. I can first define the volume into two volumes. The flux, the sum of the flux of the two volumes is going to be the same as the bigger volume because where the volumes meet, it's going to cancel. So this is a bunch of small volumes. If I zoom in, so I have volume 1, I have volume 2. Whatever flux is going out from this volume 1, right? And then I have flux coming out from volume 2. The total flux of the sum of those two volumes is going to be the total flux, right? Coming out from here and here and here. But what's happening on the boundary is going to cancel because one region is sending something in this direction. The other region is sending something in the opposite direction. They cancel each other. What remains is the flux of the outer surface. So yeah, you can divide this big volume into tiny volumes that sum up to the big volume, and the flux of each volume, when we sum it up, everything happening on the boundaries cancel, and what remains, the net result is the flux coming out of the surface, the big surface. Right? What are those small fluxes for small volume elements? That's the definition of the divergence. So intuitively, this just equals the divergence over a volume. The sum of the divergences, tiny fluxes over a volume, right? dV. Right. So when you think about it from this perspective, the divergence theorem and Stokes theorem are really natural. They're really, it's like the idea of taking a big boundary integral and divided it, chopping it up into integrals in the interior of it. So this is called the interior view. So there are two views. There is the interior view, and then there is the exterior view. What I introduced previously was the exterior perspective. This is the interior perspective, where you start at the boundary and divide the integral down into the interior, or you could start with the interior, integrating over the interior, and tie it to what happens on the exterior. We have 5 minutes. Okay, I want to talk quickly about the, I remember when we talked about the conservative field, and we said we want to go back. What's a conservative field? It's a field F where if we integrate around any closed curve, C, the circulation is 0, and C could be anything, right? Any C, any kind of curve, as long as it's closed, right? So if this is true, this field is conservative. So we said this is kind of difficult to prove because we cannot calculate the circulation around every path. There are an infinite number of paths possible, but now the curl gives us the tool to show how we can prove that a field is conservative or not. Why? It all goes back again to Stokes' theorem, right? So a circulation F dot dl, we said, is always going to equal surface integral of the interior of the circulation. It's always going to equal the surface integral of the curl of the field. So this is curl F dot ds. Okay. When is this guaranteed to be 0 always? Regardless of the path. If we have a field where the curl of this field is identically 0, meaning it's 0 at every point in space. If someone gives me a field and tells me, hey, the curl of this field is 0 everywhere, that means from Stokes' theorem, whatever the path C is, this will always equal this, and this is always 0. So this surface integral will always be 0. So whatever the path is, this integral will always be 0. So this is a sufficient condition. Give me any field and tell me its curl is 0. That's enough for me to know that the field is conservative. Let me see. The other thing I want to introduce is something called null identities. Important vector calculus identities. And the null identities are as follows. If I have a field that I obtain, if I have a scalar field and I obtain from it a vector field by using a gradient, and then I find the curl of that field, this has to be identically 0. This is identity number 1. And then identity number 2 is that if I have a field and I take its curl, and then I take the divergence of this field. So here I started with a scalar. I started with a scalar, then I got a vector field, and then I got a third vector field. Here I start with a vector field, I got a second vector field, and then I got a scalar. This also has to be identically 0. This is identity number 2. And this is really obvious. Why do I say it's obvious? What is the definition of curl F dot n, right? It's going to be limit as delta S goes to 0, right? The curl always has a circulation in it over delta S. It has an infinitesimal circulation. What did we say if we have a field that comes from a gradient? What does that mean? Right, a field that comes from a gradient. If I have a field that I get from a gradient, what does that mean? Remember, we said if we integrate from point 1 to point 2 of gradient V dl dot dl, that equals V at P2 minus V at P1. That's how we define the gradient, right? A field that we get from a gradient field is a conservative field by definition. That's because we define here we don't specify the path between P1 and P2. Any path is going to give me the same result, which is VP2 minus VP1. What happens if P2 and P1 is the same point? What happens if P2 comes and meets P1? We end up with a closed path. So this will be 0. So any field, any field that's a gradient field, that's a field that we obtain from taking a gradient of a scalar, is going to be a conservative field. Any conservative field is going to have 0 circulation. Right? So because this is a conservative field, because the curl has circulation in it, it's obvious that we're integrating over a closed path. It's obvious that this is going to be 0. The other one is easy to prove too. I'll prove this the next time. So let me stop here. So today, after this, I'm gonna take a break for about 10 minutes. I'm gonna open the door. If anyone wants to join in for recitation, we can. If anyone has questions, whatnot, we can do recitation in 10 minutes. But I'm gonna stop this here now. Stop share. And yeah, see you guys in 10 minutes. I'm gonna end this meeting now.